Hello everybody. My name is Martin Lukács and I would like to start a session of recording sessions about quantum computing without numbers. It turns out that apparently there are very many young students who have a trouble to understand some of the concepts, and therefore I will make a set of lectures. And in these lectures, I will try to explain the concepts of quantum computing without having the recourse to any mathematics, any numerical methods, or any analysis. And I will only use things like this. Now, the channel or the recording is called Quantum Candies. And the whole idea is that we will be using a bunch of candies to illustrate the problems and the principles of quantum computing. The lectures will be organized. We will start by explaining quantum information until eventually go and arrive to quantum algorithms such as Deutsch, Grover, Shor, quantum Fourier transform, and all of this without ever touching to any mathematics. Now we will have some definitions, and these definitions will allow us to later on look quantum computing as a discrete problem in a different dimension. So for this first lecture, or in general, I will have something to write where I will be describing some basic notions so that we actually know what this quantum candy do stand for. Now the first thing today, what we're going to be looking is information. Now in classical computer, the information, you can say that for a single bit, which is the basic unit of information, so we will say we have one bit. One bit can take two values, and it is a purely physical signal. It doesn't really matter how it looks like, but we can say that if a bit is white, yes, if a bit is red, now this would mean that the bit has value 0, and here it would mean that the bit has value 1, right? So now what does this mean? This means that I will have some physical quantity representing value 0 and some physical quantity representing value 1. Whether it is electrical, whether it is light, whether it is switches, it doesn't really matter. I have two discrete values or discrete particular that cannot exist at the same time. Which means if I have a bit, now this bit, if I send him from somewhere to somewhere, if I take the bit, now the bit is either 1 or the bit is either the bit is either 0, white, or the bit is either 1, which is red. Right? Okay, so it's quite simple, and if you know something about the classical logic, then you would say that this can be some particular voltage, let's say voltage 0, and this can be voltage 1. Right? They cannot coexist at the same time. Now the most important is that if we go to the side of the quantum, so let's have it like this, whiten, right? Now, if I go here and I go onto the side of the quantum, so again I will say, okay, my equivalence, here I will have some 0, and here I will have a 1, right? So again, in quantum computing, I also have I can have a qubit, so here we will have so this will be 1 qubit, right? So I have 1 qubit. And the whole idea, again, I will have the qubit will be color white for 0, and it will be red, or some sort of red, matching, for value 1. Now the difference is, one of the main difference, okay, let me see so I can turn this a little bit, like this. Okay, so the main difference what we have right here is that this guy, they cannot be in the same time and space. So either my qubit is 0 or my qubit is 1. Now quantum, on the other hand, I have to say that my qubit can be in value 0 it can be in value 1, or I can put them in the same time and space. So I will have this mirror, and I can put them in same time and space in 0 or 1. Right? So you could put here some separators saying it is either 1 or 0. Here I can have it either 1 or 0, or 1 and 0 at the same time, as you can see here. Okay, so now how does it work? So now there is a physical barrier between classical and quantum. While both classical bit and quantum qubit, they both can have discrete values of 0 and 1. Quantum qubit can take these values where both 0 and 1 exist at the same time and space. Right? But if we take it from purely physical world, we know that these two guys, we can observe them, right? If I say the light is either off or the light is either on, then I could say also here I have light is either on or off, but I can never observe these two guys here. Right? I cannot really say that light is on and off at the same time, at least not in the strict sense of light being or on and off. Yes. And so there is a separation between the classical, the discrete world between values 0 and 1, and the quantum world of values 0, 1s together in the same time. Okay? So let's move a little bit further. Let me just put these guys here. So I have 0, 1. I have here 0, 1. Yes. I have here, and here I have 0 and 1. Right? Now, so what does this mean? Now, this has a quite specific meaning. The fact that 0 and 1 can not exist at the same time and space in our classical universe implies something, that there is some rift or something special between these separate values of 0 and 1 and the joint values or the co-occurring values of 0 and 1 in the quantum world. So now what does it mean? So let's take a quantum qubit which is in value 0. Right? Now this qubit, we can even do it slightly a little bit better. Let's take a classical bit, yellow, that has value 0, or actually to have to keep the original notation. Let's take, I have some classical bit 0, and then I have their equivalents, qubit 0 and 0. Now what I want to do is I want to take the classical bit, transform it or give it value to a quantum bit, maybe do some operations, then again obtain quantum value 0, and from there go into classical value 0. Right? So now what you can see here, this is sort of very specific, because you could imagine up to here and up to here we have a classical information coming, in particular some sort of maybe circuit, yes? And actually not up to here and here, from one direction to another. Then here we will have some transformation or some information transformation that will tell us from classical bit with value 0, initiate yellow sweet quantum bit with value 0, do some operation on it, and then take this value of this qubit which is in 0 here, and transmit it back to a classical qubit, which classical value 0, and then send this information somewhere else. Right? Okay, so we have this, and so now the question is, okay, so what happens here? Now in quantum, as you can see, we already start to see the fence between classical much more precisely. We have classical information inside, sort of inside of the dimensions, or inside of the classical world, we have this quantum. And inside of this discrete quantum, we will have the non-discrete, the superposed, all the unexplained quantum, which behaves both as a wave, as a particle, that can illustrate our concept of having two bits of information at the same time. Okay, so now what does it mean? So now let's take some sweetness here. Maybe we could go, okay, let's take a sweetness yellow and pink. Yes. Now, what I do here, what I can do here, I can take this state, which is 0, and I can manipulate it to put it into, which is called superposition, between 0 and 1. Yes? So now essentially it would mean that during all this quantum time in my private quantum world, I will have the same qubit flying through my quantum world, however, having at the same time, but so if this is, let's say, step 1, step 2, step 3, and so on, I start with the quantum information of 0, I split it between 0 and 1, I am here still 0 and 1, I am here still 0 and 1, and then I join it back into 0, and I transmit my information to a classical qubit. Right? Now, as you can see, now the idea is that from the point of view of these two guys, which means from the point of view of my classical information, in here, nothing happened. What I saw only, I saw transmission of classical information from qubit, logical qubit, to this quantum qubit, which is information 0. And then here, because I know that I had 0, I obtain the information 0 here, and I transmit it to my classical qubit, and I send it away. So all of these, what happened here? Oh, I cannot see it, yes? That's why when you turn on and turn off the light, you don't see the lights being at the same time turn on and turn off, or the famous Schrödinger cat, that if you could essentially use these information to control the physical world, you will have a cat that is at the same time alive and dead, yes? Now, I will not go to too many details about how exactly this works. The idea is the part from setting it, having classical information to quantum information in causal initialization, the part of getting quantum information to classical, let's say, information is called measurement, and the most important is that here I can, from here to here, I can transmit only classical information, which is logical information, and here from here I will obtain, again, classical information, but under some probabilistic rules. Yes? So how do I obtain these guys? We will see it a little bit later, because when you split single candy to multiple states, you have to introduce the concept of mama bear, baby bear, and a whole bunch of other animals. Okay, so let's go further. So let's put these guys here as an illustration of these concepts. And let's look at one of these guys. So again, let me take a yellow guy here, and let me take a pink guy here, right? So now what we know is that what I can do, I can take a qubit, quantum bit, in state 0, I can transform it to a superposition of 0 and 1, and then I can take it back and transform it back into the logical qubit state 0, right? So now, how do I do this, and what does it mean? So for this, we need to introduce some other guys, in particular mama bear, but I don't have, I will bring back the jellies, because the jellies are very good with bears, and I will introduce some new notation here. Here I have a, so this is a baby bear, yes? It's a little candy baby bear. Now baby bear is sweet, and we will call him plus. Yes, this is a little plus. Now this guy here, this is a tic-tac or something like that, and they're minty, so they're minus. Yes? Yeah? So the whole idea now is that when I break my single state into here, they have some special properties. There is a lot of mathematical theory, whether you look at it from a spectral point of view, if you look at it from the quantum complex coefficient point of view, if you look at it from the probabilistic point of view. The general idea, the most important I want to communicate here, is that I have state 1, I have a classical state 1, and I can take this classical state and break it into some quantum component states. Now the quantum component states, they are types of superposition, and in particular, types of how you can break one state into multiple states at the same space and time, right? It's exactly here. I have a physical state 0, or I have physical state 1, or I have one state where I have the logical state as components. It's called basis states, but for now, again, I'm trying to do as far as possible from any mathematical expression, and let's see if we can get through these concepts. Okay, so, however, because I do this transformation, there are some rules that apply. Yes? And in particular, as you will see, when I break one quantum state, which is in this case 0, to some superposition of states, they get some mama bears and some baby bears. Now in particular, oh yes, I will need one more mama bear, or let's do it this way. We have here nice and pink guys. I have no idea what they are. There's some sort of sweetness, yes. And so let's say that for now, until I get my hands on sweeter bears, these guys means plus, these guys means minus. Right? So now when I break this guy, what it actually means that I will create here and here, I will create states that exist at the same time, that have some sort of values in front of them, and these values must, for some very special condition, which is called L2 norm, which means the square of these values must equal to 1. Now, why is this important? It's because when you look at this guy, you can see it, which means the guy, he's existing here physically, and we will say that it is observed with the value of, with the probability of 1. What does it mean? It's like, if I look at it, oh yes, it's here. This is exactly its value. It is observed with probability 1. If I don't look at it, and I anchor it, it's still 1. Yes? Up, up. Yes? So, its probability of being observed is 1. Yes? Same if I take the red one here. Yes? If I take a red one here, I have the probability of having value 1, of observing value 1 with probability 1. So what does it mean? If I hide it, and I look at it, and I hide it, and I look at it, it is still 1. The probability of looking at this is 1. Which means if I have a qubit with value 1, the probability of observing value 1 from a qubit with value 1 is 1. Yes? However, it gets all a little bit trickier if we do this thing. So if I have a qubit 0, yes, physical or qubit with value 0, which means this qubit is so almost equivalent under the measurement, which is right here, that if I have a qubit with value 0, then when I measure it, I will obtain, let's say, classical information 0, which means I will extract information qubit with state 0, I will obtain 0. Right? Now if I take this different dude here, my pink qubit, where is my pink qubit? Here's my pink qubit, and I put it here, and I try to extract the information by let's say, measurement, and from pink qubit, which has value 1, I will obtain classical information value 1. So this is called that you will observe from a quantum qubit, you will observe classical value. Yes? Okay. But now, how about my mama bear and baby bear here? Well, this is when it gets a little bit tricky. And the whole idea is, these guys, they exist, these two guys, 0 and 1, they exist at the same time and in the same space, but they cannot violate some rules of reality. And in particular, is that, as I was saying, if you look at the light and you turn on the light is on. Which means if you turn on the light and you observe the result, or the fact of looking at the light will determine if the light is 0 or 1, right? So now, this means that I have to apply the same rule of extracting information from quantum to classical as I do it in my classical discrete states. Right? So if I have a qubit with state 0, I have 0. Qubit with state 1, I have 1. So what happens if I have a qubit where I have 0 and 1? Well, it sort of depends on these little sweet thingies. Now, in general, I already said that all together, the two sweet guys here, they might have they have to have the L2 norm, or the sum square of them has to be equal 1, right? So it means that if I look at it from slightly or quite relatively simplified point of view, I can say I can observe, or if I apply, let's say, if I apply a measurement or information extraction of quantum to classical information from this guy here, then I will have something. I can maybe I can do it this way. Ooh, they're falling. Oh la 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 la. So what I can have, I will say that I will have square of yellow and square of pink will become my probability to either observe from this state the yellow or from this state the pink. Yes? So this essentially means that I have some magical device, it's not really magical, it's quantum measurement, that now will tell me that if I have such a signal like this, so the signal, we can see there's some sort of qubit that is flying, and you could look at that. The classical qubit, when it's flying like this. It's essentially like you driving through the, let's say, Las Vegas Strip to the cinema. It goes like this. Now it stops here. You get something, then you go to the cinema, you go something, and so on and so on. Right? However, if you are in a quantum car, now this quantum car says, I'm going at the same time in Las Vegas Strip and at the same time in Champs-Élysées in Paris. So you're just going like blah 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 blah. Now as long as you don't make any decision, you will go through both of them at the same time. But now you say, okay, I'm going to stop in Las Vegas. So if you stop in Las Vegas, you take state yellow, or you take state 1, and you are in Las Vegas. And then you will continue as such. If on the other hand you say, I'm going through both of them, and I will go to Paris, then you will transform to state 1, you are in Paris, and you continue on your way in Paris. Okay. Now, of course, there are some rules, and it is not as completely easy as to decide, oh, I want to go to Paris, or I don't want to go to Paris, because these squares here that you have here, these sweet little pink things, they will determine how you can obtain from this superposed state this guy or this guy. In particular, as I said, the square, essentially this plus this must equal 1, and it is translated or transformed directly into probability of observation, right? So what does it mean? It means that if I do my measurement experiment like I did from logical qubit to logical classical information, from classical or from here, then I will apply a measurement, and this will tell me that from this state, which is yellow 2 pinkies, pink 2 pinkies, I will have 2 pinkies probability to get yellow state. However, it will also tell me that I have 2 pinkies probability to get a logical 1 state. Right? So, of course, eventually, if I can send some information about how it works and how that you understand this concept, you can of course do more rigorous books. There is 1,000 books about quantum computing, and you can put here numbers and you see what exactly it means. So right now I say that if I apply measurement here, then I can either have an outcome yellow with the probability 2 pinkies, or I have red with the probability of 2 pinkies. Yes. Now, okay, so I have some basic transformation where I can go from yellow, pink to yellow, and so on. Okay, so now let's look at something more exciting. So again, let's take our state, yellow state, and let's say that I have a transformation that will do the following. Let's say I have a transformation as this. So where do I have some pink one? Oh yeah, here I have it. So I will say, okay, so you can see this. It's right here, yes? Yeah, let me just move all of these things a little bit up here. Yes. Okay. Maybe I should move it a little bit here, yes. All right, so yes, like this, and this. All right, so classical values, yes, discrete values, superposed values. Second concept, from classical and from quantum to classical, some separate world. Third concept, from single quantum states, I can obtain a complex or quantum state where I have component classical states with two pinkies of probabilities. And then finally, today we will see that I can take this state and I can have a transform which is called the Hadamard transform. The Hadamard transform is quite important because we'll use it in most and many of our quantum experiments, in particular Deutsche algorithm, Deutsche OSI, and all of these oracle-based algorithms. So 0 and 1. Now I have Hadamard transform, and Hadamard transform does something very, very cool. So now what does Hadamard transform do? Okay, you can only see it on one camera here, yes? Okay. All right, so what does it do? Hadamard transform will take a 0 and transform it to what? It will transform it to a superposition, so a quantum state with compound logical states. Do I have any pink one? Okay, the pink and the red one, they are sort of similar, so I will try to find more pink ones, so maybe I can do it this way. So I just put red here, and in order to be coherent, I can replace the red everywhere here. That way, it's not confusing, and you can see red everywhere. Oh my gosh. Okay, and I will take another red. I have red here. Okay, so I have a yellow, state 0, logical state 0, and my Hadamard gate can break it into compound state, exactly as we saw here. But we're not actually right now interested in the probabilities of observation, these double pinkies. So we'll just put single pinkies, because single pinkies means these are the quantum, the values to which it is, and their square is equal to 1. Okay, now where do I have some? Okay, now this is a little plus and another little plus here. Okay. Oops. Oh, what a disaster. Okay, here we go. So I have this 0 plus 1. Okay. Now I have a 0 bit. I put it here, quantum, so you can see it, like something like maybe here, yes, 0, 1. And again, Hadamard gate, it will break it to a 0 plus a 1. However, now this is a big however. This single change is at the basis of so many important properties in quantum computing that it is almost impossible to emphasize how important it is. All right. I have to find out a better method how to deal with my candy. And so what does it do? It actually takes the 0 and breaks it in 0 minus 1. Yes? So it's a different representation. It transforms 0 to 0 plus 1 and 1 to 0 minus 1. Yeah? Okay, so this is where we will leave it for today. We saw from classical information to quantum information. We saw there is some initialization, there is some measurement. We saw the principles of obtaining a quantum state, or the idea that the quantum state is represented by some complex magnitude that becomes a probability of observation. And then we saw that the basic quantum gate right now is Hadamard, that breaks 0 to 0 plus 1 or 0 minus 1. All right, so thank you very much. And I'll see you very soon in the next episode of Quantum Candies.